Hi everyone and welcome to another lecture. Today we'll be talking about vector spaces, which will be at the very center of our discussion in linear algebra. So the first question we ask is that what is a vector space? Now if you are someone who has freshly taken a calculus course, you might say it's a space where the vectors live. Well, to some extent this is correct, but we will see that by the term vectors we will mean not just arrows that have magnitude and direction, but we can actually generalize this concept. So to give an idea what a vector space is, we'll start with some definitions. So the definition will be: a vector space or a linear vector space is a collection of objects. So we write, a vector space is a collection of objects, and we denote these objects with our bracket notation. Let's say this is object number 1, this is object number 2, and let's say da 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 da. We have a final object as V, and here we are using the ket notation, that is something we called the ket vector. And let's say we denote our vector space, the vector space, with calligraphic V like this, though it doesn't look like a bit calligraphic V, but let's just think of this as a calligraphic V. So our vector space calligraphic V is a collection of objects like this, and we are calling them vectors. So it's a space that is a collection of vectors, for which, that is, if I have this object, then for which, number 1, a definitive rule or a definite rule of addition exists. This means if I have some vector V that belongs to some vector space calligraphic V, and some vector W that belongs to this calligraphic V, then if I add them, this addition also belongs to this calligraphic V. So this is property number 1. And the second property in the definition is that a definite rule for multiplication. Oops. So remember that we introduced the concept of fields earlier in our lectures. So when we want to define a vector space, we also have to define over which fields we are constructing this vector space. So the field is there first, and then we are putting some extra structure and making it a vector space. So let's say I have some scalar that belongs to some field called K. Alright, it can be real, it can be complex. And for our discussion on linear algebra, we can restrict ourselves in the most general case in the complex scalar field, that is the complex numbers. So this scalar multiplied with the vector, this belongs to the vector space and this belongs to the field. This whole thing will belong to the vector space. So these are two definitions, two properties that comes from the definition of a vector space. So if you have some objects, and by objects I mean they can be anything, let's say numbers, let's say column matrices, row matrices, square matrices, or it can even be functions, and we will see some examples of it in the next lecture. But for now we want to treat them in a very abstract sense of manner. So whenever we have a collection like this and I take any two random elements, I add them, I get another element that is already exists in the same space. Then I take one of the elements and multiply with a scalar over which the space I want to define, and I also get another element. You can even call this, let's say, v prime, this a times vector v. This also belongs to that particular space, that is calligraphic v. So if any set of objects satisfy these two definitions, then we can say that they form something called a vector space. In fact, from these two definitions give us the following features. I mean, not these two definitions, these two properties coming from the definition of vector space give us the following features. So the features are, the first one is called closure. So what does this mean? This means the addition is commutative, because if I take two elements that belongs to the vector space and if I add them, this is the same as if I just reverse the order. And if I had, let's say, three things, v, w, z, I could write it as z, w, v, and so on. So this only means that addition is commutative. So that's what closure is all about. The second one is scalar multiplication is distributive among the vectors. So the second feature is that scalar multiplication is distributive among the vectors. This means if I have a scalar that belongs to the field over which the vector field is vector space is defined, and I have two vectors that belongs to my vector space, then A of v w is just a v plus a w. This is what the distributive property is, that is the distributive property of the scalar multiplication. And then we can see another property, that is scalar multiplication is distributive also in scalars. This means if I have two scalars, a, b belongs to k, that is our field, remember this is the field, then a plus b times the v is just av plus b v. The next property or the next feature is that our multiplication, that is our scalar multiplication, is associative. That means if I have some scalar a, b belongs to k, then a times b of v, that is first you multiply b with v, will be the same as b a v, and this will be the same as a b v. So this means this, whenever you have this associativity property, you know that these brackets don't matter. And the fifth feature that we will see is that our addition is associative as well. That means if I have three vectors, and by addition I mean the vector addition, so if I had something like this, this is just equals to this. So again you can see that these brackets, they don't matter. And the sixth feature that we're going to see now is that there exists something called a null vector. So the existence of null vector. Now this is particularly important for every vector space there exists some vector called 0. This is something we are calling the null vector. And because of this null vector, we can write this null vector times any vector. Let's say A belongs to the vector space and 0 belongs to the vector space. This 0 ket is equals to just A. So this guy, that is this null vector, acts like something called additive identity. So that means whenever you add something with the null vector, the thing that you are adding, it doesn't change. So that's why it's called an additive identity. And because of this null vector, we also get another feature, and this will probably be our one of the last features. And let me just change the color a bit. So finally, because of this null vector, we can ask, can we find something? Let's say I have vector A and I want to find something over here such that this gives me a null vector, right? The answer is yes. There is something like this, and this is something called the additive inverse, that is minus A ket. This is called additive inverse. So whenever you take the idea of additive identity, you also get as a bonus the additive inverse. And now you might think that, oh, all of these are really complicated because it's a long list of features, right? But a very simple idea is that do what comes naturally. This is a nice mnemonic. This is by Ramamurthy Shankar in his book called Principle of Quantum Mechanics. So to quote him, do what comes naturally. And whenever you think of these properties, it's a good idea for the beginners to think of these kets as arrows and try to compare them. That is, the properties you know for arrows, whether they match with the criterions you just saw in this video. And the reason we are generalizing so much, or we are going from this idea of a vector like an arrow to another idea where the vector is something really abstract, because you can see that let's say I have a vector, the arrow vector, let's say A prime, as 2i minus 3j, right? And let's say I have another vector called B, and let's say it's I plus 2j. Now if I add them, then we have 3i minus j, right? But notice something. This is a vector, that is this A prime and B vectors, both of them belongs to this xy plane, right? And whenever you add them, this also belongs to the xy plane. And even if you scalar multiply any of them, it will just get a bit rescaled. That is, if you just evaluate 3a prime, this is just 6i minus 9j. But then again, it also has this components, that is x components and y components, and it doesn't add any z component, right? Or some other things. So the structure, the way they look is the same. In an abstract sense, you should call the structure. So this also belongs to the xy plane. And you can see that all the other features that you saw over here, these are also true. So the key point is, whenever you are asked to verify whether a set of objects form a vector space or not, you should always check these two things, that is the addition property, that is in this one. Let me circle that up, this one. So this should be number 1, and the second thing is this one. And if the set of objects satisfy these two conditions, the rest of the features they will satisfy most of the time, but it's always a good practice to check whether all of these features are satisfied or not. And the reason I was discussing this A vector and B vector over here is that this is the addition of vectors that you guys are familiar with. Now think of two functions. Let's say f of x, let's call this x square, and let's say I have g of x, let's call this 1 minus 2x, and let's just add them. The addition will give us some new function. Let's say h of x is just x square minus 2x plus 1, right? But this is also a function. It has not turned into something else. So whenever we talk in terms of vector space, these two ideas, that is this idea from here, let's say idea 1, and this idea 2, when we talk in terms of vector space, these two ideas will be seen as the same thing. So this is where the power of discussing the vector space lies, because you are generalizing everything and you are not considering any kind of representation. So this will be it for today. I hope you got the definitions and the proper motivation on why we want to study vector spaces. In the next lecture, I will discuss some examples of vector space, and I will also try to discuss a counter example of vector space. And by counter example, I mean a set of objects that will not form a vector space. So thank you, and I'll see you guys in the next lecture.